Thank you so much for the invitation. It's a really great pleasure to be here. So what I would like to talk about today is an ongoing project with a few people, most notably Vadim Kaloshin and then other people around that we mentioned who each result belongs to in the course of the seminar. But first I would like to talk about what I will describe today. So I will study a problem which is what I call dynamical inverse problem. It is a version of a classical problem which if you want is a length spectrum determination, length spectrum rigidity, but for billiards rather than manifolds. Okay, so that's let me define what the main object will be. So a mathematical billiard for me for today is going to be an open subset of R2 and in order to define a billiard, well, I need this to be connected. I need the boundary of this set to be sufficiently smooth. And let me just write it like that. Finitely many smooth curves. And smooth means, in order for it to be defined, I need C3, but you probably want to think about it to be C infinity. Doesn't change that much. And these curves are simple and closed. All right, so I have a couple of models in mind I would like to describe. And one is called Burke of billiards. And I want to think of omega as some convex domain in R2. So omega is convex. And actually, I will ask a little bit more. I will ask it to be strongly convex, which means that not only it's convex, but the curvature at any point is strictly positive. So actually, for me, this is actually strongly convex. But I will not talk about anything else, so I will not mention the word strongly anymore. And again, the curvature at any point is strictly positive. And so the domain itself is this oval shape here. And the other model which I would like to keep in mind is, would like you to keep in mind, is the setting of hyperbolic billiards. And I have a specific case in mind, which is an open billiard, in fact. So I will just consider omega to be the complement of a finite union of strongly convex sets, compact sets, which are called the obstacles. So the idea that the picture that you want to have in mind is something like this. So I remove a bunch of convex things from the plane, and I play my billiard on the outside of this. Okay. So this is the setting. Just two examples of what these open sets are. And then what we want to study the billiard flow. Which is just, well, if you want the linear flow inside the domain, so it's a constant velocity in omega, and then I need to tell you what happens when you hit the boundary. In the boundary, you have elastic reflections. Which means that if I have, for instance, a boundary which is like that, I have an incoming trajectory with this angle, then I have the angle of incidence will be equal to the angle of reflection, and the flow continues back inside the domain. This is the boundary. And this somewhat explains why I need some smoothness. Otherwise, if I have a corner point, it will actually cannot be defined after the collision, and it will die there. So this is, again, some general setting. And then what is the question that I want to ask? The question that I want to ask is that, OK, let's study some very specific trajectories in this billiard flow, which are periodic trajectories. So what I will focus on are periodic orbits, which are, well, essentially closed geodesics. OK, so they are orbits which, after some finite amount of time, come back themselves. So for instance, I can draw something which looks like a period 3 orbit here, and something which looks like a period 3 orbit there. Okay, so periodic orbits can be proven to exist in both of these cases in some different flavors. And one thing that one can associate to a periodic orbit is its length. So how much we need to wait, assuming that it is a unit speed, for instance, going throughout the open set with unit speed, how much we need to wait until I come back to the same position with the same velocity. So to each periodic orbit, I can associate the length of the corresponding trajectory and I can construct the spectrum of all such lengths. That's what I'm going to call Ls of omega is the set of all lengths of periodic orbits. There exists a periodic orbit of period L, of length. Let's throw in multiplicities. I think there are some ways to call the set without multiplicities, which is the length set. But let's throw in multiplicities. So this is going to be, this is called the length spectrum. And the question that broad question that I want to ask is how much of the geometry of omega is encoded in this set or in this spectrum. So of course, this spectrum is invariant if I rigidly move my set around. So in all what is going on next, I will essentially consider not domains, but equivalence classes of domain where I move by isometries. So everything that I will say will be mod isometries. And for R2, it just means rigid motions. So the question, which is the dynamical inverse problem, if you want, or the length spectrum inverse problem, is how much about omega is very complicated. It is rather complicated. Yes. So, well, in the first example, one can actually prove that this set has accumulation points which are multiple of the length of the boundary. That's about it, but it's still a very complicated set. And in fact, there are some asymptotic expressions which can be extracted from the length spectrum, which are related, which are called Mervisian-Rose invariant, and they are related to, well, another question which I am about to talk about.
How do you record the multiplicity? Couldn't you have infinitely many?
That's a very good question. So it turns out that you can definitely have infinitely many of them. However, if you have, for instance, one parameter family, you will have to deal with that. So you can actually have very complicated sets as multiplicities. In fact, one way to get out of this problem is to consider make some extra work and not consider only the length spectrum, but consider a marking on the length spectrum, which I will mention in a little bit. But for the time being, let me just gloss over this problem. Okay. So how much about omega is encoded in the length spectrum of omega. In particular, can I recover omega from the length spectrum? Okay, so there is a very classical question which is very intimately related to this, and to a very superficial level, it's also philosophically related to this, because if you, rather than playing classical billiard, you play quantum billiard, then the periodic orbits would be the eigenstates, and the natural object to look at would be the eigenvalues corresponding to these eigenstates. And so the quantum question of this is, let's have a look at the spectrum of the Laplacian rather than the length spectrum. Fix your favorite boundary conditions. So this is the spectrum of the Laplacian. With some boundary conditions given BC. And then you can ask the same question about how much about omega is encoded in the Laplace spectrum of omega. And it turns out that these two questions are not only philosophically related, but very intimately related because of trace formulas. So for hyperbolic manifolds, for hyperbolic surfaces, there's a Seilberg trace formula gives you exactly, essentially, a dictionary between, well, not a dictionary, but it tells you that if you know the Laplace spectrum, you can actually recover the length spectrum. And this was so you have Seilberg in 56, and later on for domains, it was actually proved by Anderson and Melrose. In 77. And what these trace formulas say is that if you, for instance, consider the spectral measure associated to the Laplacian, then this would be a smooth distribution except at a set which is precisely the length spectrum. Well, not quite, I'm cheating. It's the length spectrum, it's the closure on the length spectrum counted with multiplicity. It's counted with multiplicity in the sense that I take every multiple of an orbit as an acceptable orbit. So I can trace this 5 times, and I consider 5 times its length. Okay? So that is what the trace formula relates. And in particular, they prove that under generic assumptions, as the Laplace spectrum of a domain determines Yes, that's correct. So yeah, so I'm cheating a lot. So over here, you would actually consider the resonances, but there is a dual theory which you can play around, and in fact, there are some results in the Laplace spectrum business. But as far as I understand, it's a result by Zeldich 2008 and 9 something, which relates some resonances of the Laplacian to the shape of a system of 2 scatterers like this, except they don't have a third one. But generically, this object determines the length spectrum via singularities. Okay? But in fact, it encodes much more information a priori than the length spectrum. For instance, one can recover dynamical quantities after to the Laplace spectrum. So if you consider again a spectral measure, you will have some singularities over here, but there's an asymptotic expansion at this singularity which tells you something about the dynamics. For instance, it will tell you the eigenvalue of the Poincare map of the billiard flow when you flow around each orbit. So there's a lot of more. Is there a question?
Yeah. So does this stuff also work for polygonal billiards?
That's an excellent question. So there is a theory about these kind of questions of polygonal billiard. As far as I understand, you can recover the angles of a polygon, but not the shape of the polygon itself. That's the most, I think, recent result that I am aware of, which is relatively recent, about 3 years ago. So,
you don't have periodic orbits.
well, you have families of periodic orbits on polygonal billiards.
So you use triangle, but what can
Okay, an obtuse triangle is quite a weird object, but if you take some skewed pentagon of sorts, you can still figure out the angles, but there are some non-isometric classes of pentagons which share the same angles. So there's something you can recover by completely different means from what I'm about to talk about. All right, so this is essentially telling you that one can study the dynamical spectral problem, the dynamical inverse problem, by studying the Laplace spectral problem, which has a much longer history. In a priori, this problem is problem of studying length spectrum determination or length spectrum rigidity, which I'm about to define. It's a little bit more complicated than studying this because these contain more information. For instance, it's well known that Wade law tells you that you can recover the area of the domain by the Laplace spectrum, but it's unknown if you can do that with the length spectrum. So there are some quantities which...
It's not known?
No, it's not known in general.
What about one-parameter family deformations?
That's precisely what we'll talk about. So I have in the title of rigidity and determination. One parameter family is rigidity. I'm about to define what I'm talking about.
Just as background for just a one-parameter family of convex Burke billiards.
It was not known until our result.
The area is determined.
No,
The area is rigidity.
The area
rigidity.
rigidity.
About the area, because you were talking about
Area is not known. I don't think there is any knowledge about it. It's surprising, but that's just what it is. But that's a good question. I mean, one can study that. Anyways, let me go back on track. So if you want to study dynamical rigidity, you can borrow some results from Laplace rigidity, which is what I'm about to do. So the most crucial result, well, not most crucial, but there are some results about surfaces and manifolds which are due in the went up in the 80s by Marie-France Vignerin. That's 80, and then you have Tsunada, 85, and they constructed countable classes of manifolds. Actually, Tsunada managed to construct countable classes of manifolds which have the same Laplace spectrum, but they're not isometric. So they answer the question, well, there are isospectral classes or isospectral sets of two manifolds which are non-trivial. Essentially what they do is you start from a surface and then you cook up two different coverings which have the same Laplace spectrum, but they cannot be isometric. That's the general construction by Tsunada, which has been then employed in many different other settings. And one can transfer these to the world of domains, and that was the famous paper, One Cannot Hear a Shape of a Drum, by Caroline Gordon, Webb, and Wolpert. 91, and which says that there are isospectral sets of domains in R2 which are not non-trivial. And these sets look like triangulation of the surfaces which these guys constructed, just flat out. In particular, there are examples of isospectral domains which are not isometric, which are neither smooth nor convex. They are piecewise linear, if you want, but they are neither smooth nor convex. So the question looks like we have a negative answer, but then, of course, when you find a question which has a negative answer, you can do something where you can either pay more and assume a little bit more, or you can ask for less. So let me do both of these things. Not at the same time. So one thing that you can do is to ask for, is to pay a little bit more. And rather than dealing with a length spectrum, you can add a little bit of combinatorics to it. You consider the mark length spectrum. What is the mark length spectrum? So MLS is the marked so for instance, in the class of manifolds, rather than considering the length spectrum itself, you consider the map, which takes each free homology class and maps it to the geodesics corresponding to that free homology class, which has that length. So this map defines a marking of this set, and which I call the mark length spectrum in the case of manifolds. In the case of Burke billiards, I can mark each periodic orbit by a dynamical quantity, which is the rotation number, so how many times the orbit turns around the domain divided by the period. That's the rotation number, and it's going to be something which is rational, say in 0, 1. And this corresponds to a marking of each periodic orbit for the Burke billiard. And in hyperbolic billiards, you have a coding which you can, if you want, you can call the scattering sequence. So each of these orbits which will hit these scatterers in some order, and you record this order, and it turns out that by hyperbolicity, each infinite sequence which is admissible will correspond to a unique periodic orbit. You can mark these orbits with this space. So in each of these cases, you add some information, and you expect to be able to get some more out of it, which is the case. So Tal and Crook independently in the 90s, actually in 1990, proved that you can recover the metric on a negatively curved manifold of dimension 2 by the mark length spectrum. Variable, yes. Yeah. Of 2 manifolds with a negative curvature. And so if you know the mark length spectrum, you can construct the metric. And very recently, Colin Guillermo.
What would you mean? Like for every sequence, you can construct a metric?
Pardon me?
If you know the
mark,
you know the metric up to a sum.
Like we said, you can construct it.
you can define a metric knowing the lengths, which turns out to be the length.
Is it existence, or it's if you're given a sequence of number?
If you're given a mark length spectrum of a manifold, you can recover the metric.
If you don't know that there is do you know that there is at least one?
No. I mean, if you just give a random map
So it's
on R.
a kind of uniqueness state.
It is a uniqueness. Yeah, this says that the marked isospectral sets of 2 manifolds.
He's asking a question. If I give you a sequence of real numbers, I don't know what's the image of the map from Riemannian surfaces to the length spectrum. You don't know the image. You're saying if 2 of them have the same lengths, then they have to be the same by a constructive argument, by mass.
It's at least the argument by Crook it's very elegant, and you can actually construct the area of each hyperbolic rectangle by knowing these lengths. And lately, very recently, I mean, Guillermo and Lefebvre extended this result. This is in 2018, and they proved that the same holds locally on n manifolds. So those are manifolds who carry nanos of geodesic flow. Okay. And local means that, well, maybe there is some other manifold very far away which share the same arc length spectrum, but for each manifold there exists a neighborhood, so that if you're given the arc length spectrum and they coincide, then they must be the same manifold. Okay? So that's what you get if you pay a lot more. But then, of course, you can also ask a little bit less, and you can ask a question about deformations. So I didn't define what an isospectral set is, but it is, so let me define what an isospectral family is. A set of domains, a family of domains, omega t. Let's say that I am in some global set of domains M. For instance, the Burke billiard, for instance, hyperbolic billiards, for instance, you name it. So you have a one-parameter family of domains in your favorite set. Is said to be isospectral if, well, if you take any two elements of this family, they have the same length spectrum. What is, of course, asking. Well, you can call it marked isospectral families or length isospectral family. However, it turns out that a simple argument, which ultimately is Sart's lemma, tells you that a family is length spectral isospectral if and only if it is marked length spectral isospectral. And the argument essentially goes as follows. LS, you don't know what it is, it's an ugly set, but you can construct it in a variational way. So as a set of critical values of some function, which is at the end the action of or the length, if you want. So since it's a set of critical values of some function, it has got to be a zero Lebesgue measure. But now if you have a function which maps into a set of zero Lebesgue measure, and you deform this function a bit, well, it must be actually, the deformation must be constant. So whenever you have a family of LS isospectral domains, they're automatically MLS isospectral domains. This actually is a really important observation, which makes essentially the study of isospectral families much easier because it comes for free with a marking. Well, the marking is unknown. You don't know which orbit corresponds to it, but you know that each orbit will have its length preserved across the deformation. Okay? So in this setting, you expect to get a bit more, and in fact, you get more. You can ask whether or not there exist non-trivial isospectral families, and it turns out that in the 80s, yes, in the, let's see, in the 80, Agimi and Ekasdan proved that there are no non-trivial isospectral families of two manifolds, and later on negative curves. And later this was upgraded to n manifolds by Kroke Sharafutinov. So that this problem is a problem which we call spectral rigidity, as opposed to spectral determination. So you cannot deform a domain by preserving the spectrum, or you cannot deform a manifold by preserving the spectrum. But what is the situation for domains? Here the situation is a little bit more complicated, but if you add a little bit more, you can actually get something out of it. And before stating our result, I would just like to mention the result by Zeldich. So I mentioned these sets, which are isospectral, are neither smooth nor convex. So it's kind of natural to ask what is about for convex smooth domains. And Zeldich in A08 proved that if you consider M to be a class of generic analytic axially symmetric convex, that's a lot of hypotheses, domains, then this Laplace spectrum of omega determines the domain in this class. It had more hypotheses.
I mean, but the analytic idea is to use the complete asymptotics around one orbit.
Yeah, so the analytic idea is actually, yeah. So it's a big cheat. So analytic is necessary because what Zeldich does is essentially to consider one orbit, a period 2 orbit, which does this. And by studying the asymptotics of the spectral measure, which I mentioned before, is able to recover essentially the asymptotics of a curvature, the jet of the curvature at this point. And then by analyticity, you it's a complete, very clever cheat, which is 60 pages. So that's what it does. And as I mentioned, this result has a dual version in the resolvent of the Laplacian business, which says pretty much the same with the same assumptions. And lately, Ezari and Zeldich last summer proved that ellipses are spectrally determined among every C infinity convex domain. No, actually not convex, every C infinity domain. And in order to prove that, well, they use some dynamical properties, which is integrability, which I won't talk about. But again, this is a very recent result, and still for just ellipses, not even analytic, not just analytic, but this is just for ellipses. So up we come to our results at last. So you have actually 2 results, one in this setting and one in that setting. So the first one is a joint work with Vadin and Xiaoling Wei. This is 2016. And so it's some kind of ideally modeled upon this. So the class that I'm interested in now, convex domains, smooth. In fact, even finitely smooth, if for what it's worth. Z2 symmetric. Oops. Domains. And the result that we want to, that what we prove is actually have spectral rigidity, which means this, for any domain which is sufficiently close to a disk. So every or rather close to any disk, it doesn't matter, of course. So if any family, any length spectrum isospectral family in M is trivial. Particularly, you cannot deform any such domain along a smooth curve in the space of convex smooth Z2 symmetric domains close to disks and preserve the spectrum. Okay? And the second result in this setting is due to, well, myself, Vadim, and my ex-postdoc, Martin Leguille, 2019. It says the following. So I need to modify a little bit this picture so that it fits the hypothesis. So I need some symmetry again. And the symmetry that I want is that there is this guy, let's call it number 1, has an axial symmetry, reflection with respect to this axis. And then number 2 will be its mirror image with respect to an orthogonal axis. This is number 2. And number 3 can be anything you want with some dynamical conditions. So here, that is what I will call a Z2 cross Z2 symmetry. But it's just for 2 scatterers. This sounds like a very weird hypothesis, but the idea that I want you to keep in mind is the following. What you really want to do is to determine the...
So you don't have that third disk down.
I have the third disk, but the third disk is necessary for dynamical reasons, because it's very hard to play billiard if you just have 2 disks.
Yeah, I don't see how much you can do without it, yeah.
So you need some...
That has to be symmetric too, right?
No, that can be anything.
Okay.
Yeah. So the reason why this is somehow, the hypotheses are so biased towards 1 and 2, if you want, is the following. What I really want is to find what the geometry of 1 and 2 is. In order to do that, I need a third scatterer to define the dynamics. And then as a byproduct of the construction, I'm actually also able to cook up the geometry of 3. But really what I want to focus on is to study these 2 guys. And how do I do that? I want to shoot some trajectories, and I need a third guy to bounce from.
But 2 is just a mirror image
Yeah.
of 1, right?
So you just have one thing to determine, which is precisely the setting in which Zeldich extended by duality his result. So
You can't do the torus and the exterior scatter, right?
no, we need a third. Okay, I will tell you what I need. So you can probably cook up some things, but you do need a third scatterer to prove what I'm about to state, which is now I have my M is hyperbolic billiards, hyperbolic Z2 cross Z2 symmetric analytic generic and non-eclipse. Then we have MLS determination. Which means you can record the geometry of each of the scatterers from the Mark-length spectrum. I need to tell you what an eclipse means. It's a very...
This analytic seems to give away that this comes from a local analysis.
So yes, there is a catch here. So this is an open system. It's very easy to cook up trajectories which just escape to infinity and never come back. In particular, any orbit which bounces on the dark side of each of these scatterers will fly off to infinity. So there are no periodic orbits which visit the exterior of the domain which I'm about to.
Cover the other one.
So over here, this is the dark side of my billiard, and there's no periodic trajectory which visits that. So if I have a C infinity,
No way you can.
I can do whatever I want in the green part. And
Theorem's just
yeah. So ideally, what one would like to do is to recover the geometry here. But even here, you have a lot of holes because periodic orbit form a counter set in phase space. So what I can get is a projection of a counter space in configuration space, which might have full measure or not. It depends on the geometry, and it's very tricky. So a priori, it's more natural to add the analytic assumption to this setting to get some reasonable result. But what we really would like to do is to say that on this projection of a Cantor set, we can record a curvature at each of these points, which we are not able to do yet. But what we can do is to record the jet of the curvature at this point, that by analyticity suffices by the same argument as Zeldich. All right. And non-eclipse, again, what does it mean? The definition is very simple. So take any pair of scatterers and take the convex hull. Then any other scatterer does not intersect the convex hull. That's a dynamical condition which is very classical, and we need it to some extent. That's why I put it in green. Genericity here, again, it's very similar to the genericity in Zeldich. We require that there is some non-trivial hyperbolic twist for that orbit. And the symmetry is, yeah, we need the symmetries for.
So can you comment about the symmetry in the previous two results? What's the role of the symmetry?
OK, I can. Let me give you a very rough cartoon of this proof. So let me start from a Z2 symmetric domain. So as I mentioned, the length spectrum rigidity it's equivalent to Mark length spectrum rigidity. So I can just focus on MLS rigidity. And in particular, I can do even more. I can consider a particularly nice set of periodic orbits, which correspond, if you want, from geometrical perspective, to simple geodesics, geodesics which don't intersect. And let me draw a picture. So there will be trajectories or periodic orbit which will go exactly once around the domain and come back to the original point. And I want them to be symmetric, so they emanate from the intersection with the symmetry axis with the domain. And they are indexed by the number of reflections, the period of the billiard map. So what I have now is that I have a very reduced set of orbits I'm looking at. And since I have MLS rigidity, I know that each length of each of these orbits will be constant throughout my deformation. So what I have a map from n, if you want, actually n bigger than or equal to 2, because I don't have a periodic orbit of period 1. The least period is always 2, the bouncing orbit. I have an MLS in this case. I even consider a reduced version of it. And this tells me what the length of each orbit of period q, rotation number 1 over q, goes to. So I take q, and I map it to the length of the orbit of rotation number 1 over q. And then what I ask is, OK, this is a map which depends on my domain. In particular, I can associate to each domain its curvature, which is just a periodic function on a torus. And then I can ask, OK, let's take rho, the curvature, and map it to the space of such functions. Then what we can do, so this is a very intricate map, because if you have a curvature, you can cook up a domain. With the domain, you can cook up these periodic orbits. Again, it's a variational problem. And with these periodic orbits, you can cook up their lengths as their critical values of the corresponding function. And then what you want to do, you want to prove that when you consider the linearized problem of this, so if you perturb a little bit the curvature, you perturb a little bit your MLS. And what you want to show that this is in fact a well-defined operator between some spaces, and this operator is injective. So in geometry, this is called the Xray transform, and for billiards, it's some operator which can be written explicitly. So what we can do is that we show the following proposition. There exists XY Banach spaces So that, for instance, C8 functions is X, and C0 sequences sit in Y, with the property that T of X, so if I take a C8 deformation of my curvature, maybe C6, but who cares? If I take a C8 deformation of my curvature, then I will get some deformation of MLS, which is just a sequence, right, of positive numbers, which lies in Y. And T depends on, well, continuously on rho. So T is the linearization at a given curvature, and this thing depends continuously on the curvature, this operator in the operator norm. And last but not least is that we show that T is in fact invertible. Well, we need injectivity, but we prove a little bit more. It's invertible if rho is constant. And in fact, if you try to do without the symmetry, you find that the kernel of this operator is by no means 0, but it's given by all odd functions for a disk. That's quite a big kernel to kill. And therefore, we actually need Z2 symmetric to make sure that you don't have odd deformations, because you cannot possibly preserve the symmetry with an odd deformation. You only have even deformations allowed. That takes care of the kernel for the disk. And by continuity, you have injectivity in a neighborhood. OK? So that's in a nutshell is what our proof is and why we need a symmetry. It's a very tricky assumption to get rid of. A couple of observations which I'd like to make before giving you an idea of the second result is that this T, as I mentioned, is very explicit. Again, in the geometrical setting, this is just the Xray transform, which amounts to take an integral around the geodesic. Here, you can actually write explicitly what it is, and it is so explicit that you can actually ask an undergrad to do some numerical experiments. And over the summer, Shanza Ayub managed to, she ran some numerical simulation in Python and proved that ellipses of eccentricity less than 0.3 are spectrally rigid. Well, there's some evidence numerically are spectrally rigid. For ellipses are a very funny beast. As a billiard, you can actually write everything in terms of elliptic integrals. In particular, you can write T with some monster matrix of elliptic integrals, which you can feed a Python program, and you can cook up a check whether or not this infinite matrix is invertible or not. And numerically, she found that until you hit 0.3 eccentricity, these things are invertible. And another result which I want to mention is work with a master's student here in Munro. Well, this is, everything is done. We just need to write down things. But he actually cooked up a computer-assisted check for the SR. So what this program does, you feed it with the Fourier expansion of your curvature, of your favorite domain. It will crunch some numbers, check if this operator is invertible, and if it is so, it will tell you. And this is computer assisted. This is, in fact, the mathematical proof. Everything is done within bounded area.
When suppose you, West Wells, were able to prove this rigidity by inverting this operator, would you then be able to, in the space of domains, show that isospectral or isolength sets are isolated because they're compact, then you would get a finite, which is I think the correct.
That's your conjecture, I guess. No?
Yeah, but that's the correct conjecture that all these sets are finite. You mentioned those counterexamples.
Yeah, that would be it.
So the right statement would, you can hear the shape. The only finite element runs that sound.
Yes. And in fact,
and that would come from compactness and isolation.
Yeah.
So the question is when you're proving this inversion of this operator, are you proving it's isolated in some topology?
So I want to say a couple of things. The first thing is that we can prove a much weaker property if you're not close to a circle. If you're not close to a circle, we can prove that the kernel is finite dimensional, which is still something. And the reason it works for the circle, it's essentially, you can write explicitly what happens for the circle in Fourier modes, and you find that Möbius inversion is what you need to cook up an explicit inverse of this operator for the disk. So it's a quite peculiar reason why this operator is inverted.
For any? Is finite rank?
Yeah, finite rank for any. Yeah. Finite rank for any. So it's way stronger than this, but I just want to.
Is there a bound on that?
You can cook up a bound in terms of the C6 norm of the curvature. It's probably not optimal, but. OK, so this is a rough sketch for this half of the board. Now let me tell you in the remaining 7 minutes what's going on in the other half of the board. Here we use a relatively different technology, but what we do is very much inspired from Zeldich. So Zeldich, what he does, as I said, he fishes out asymptotics from the spectral measure singularity expansion and gathers information about the dynamics. And we do exactly the same, but rather than using the spectral measure expansion, we use the MLS expansion. Let me give you an example of how we can recover a relatively strong dynamical quantity out from the Mark length spectrum. So, for instance, what I'm about to try and convince you is that the Mark Lyapunov spectrum is an MLS invariant, so it's determined by MLS. So Lyapunov spectrum is just, if you take an orbit, say the orbit which does this trajectory, and you compute, if you want, the Poincare section when you hit the third scatter, if you want, then you get a map. This map is an element of SL2R. You can compute the eigenvalues. They turn out to be inverse of each other because it's in SL2R, and this matrix, it turns out to be hyperbolic. Otherwise, I would not call this hyperbolic billiard. And you can recover that eigenvalue out from the MLS. And how do you do that? So here's the thing. So this is actually true for, let's take two scatterers, and let me try to convince you that I can recover the Lyapunov exponent of this trajectory, which is encoded by 1, 2, and bounces to 1, 2 periodically. Okay? Now, how do I try and get the Lyapunov spectrum? Let's throw in the third scatterer. Once I throw this in, I can construct an orbit which is called the homoclinic orbit. This is not a periodic orbit, but it's an orbit which starts off to 3, bounces to 2, and then keep bouncing between 1 and 2 indefinitely. So the coding for this would be 3, 2, 1, 2, 1, 2, 1. So this is not periodic. Here you can put whatever you want in the past. It's not periodic, but it just geometrically it converges to the yellow. Well, not quite, but it approaches the yellow segment. And then this is not periodic, so I don't have any information about this in the Mark length spectrum, but I can truncate it at any length that I want and make it periodic. So by making this periodic at, say, length 2n plus 1, or maybe 2n plus 2, I obtain some orbit, let me call it hn. So this truncation corresponds to some point in this very long sequence of bounces. I have a bounce which is a right angle, and then I go back and I bounce back here with a right angle. These orbits turn out to be palindromic, and palindromic symmetries are associated with right angle at the symmetric points. Essentially because right angle is what corresponds to time inversion in billiards, and when you have a palindromic sequence, you are saying that it's symmetric with respect to time inversion. Anyways, any one of these orbits will be present in the set of admissible periodic orbits, and therefore their lengths will be encoded in the length spectrum. And then let's have a look. What would be the length of Hn? Well, as n goes to infinity, what will happen is that that white segment will approach more and more the yellow segment. So the asymptotic behavior that I'm expecting is something which grows like n times the length of the periodic orbit 1, 2, the yellow periodic orbit. So it grows linearly with slope equal to the length. And then there is a term of order 0, which I can always obtain by taking, for instance, these guys, taking the limit, subtracting that, obtain this. And then what I'm left with is some corrections. Now these corrections take into account the fact that I'm not really hitting the boundary at the endpoints of 1, 2, but close by. And so close by, you can imagine that you can, in fact, express the length of this segment as length of the yellow one plus some correction, which has got to be quadratic because this is a critical point of your length function. And how do these orbits approach the yellow trajectory? Well, they approach it exponentially fast with a rate of convergence, which is exactly the Lyapunov exponent of your periodic orbit. So the correction that I have here is some number, c, times the Lyapunov exponent of my periodic orbit to, say, minus 2n. And this 2 comes from the fact that I have a quadratic form. So you can see that now by taking appropriate limits and logarithm and whatnot, I can extract these logarithms out of the expansion for the length spectrum, for the marked length spectrum. And you need them to be marked, otherwise I cannot distinguish which one correspond to this specific periodic orbit. Now, once I have determined the Lyapunov spectrum of my periodic orbit, I can actually cook up the same construction, and so this hopefully convinces you that I can find the Lyapunov exponent of 1, 2, but a similar construction tell you the Lyapunov exponent of every single periodic orbit. In particular, they tell you Lyapunov exponent of these guys over here. And these leave very close to 1, 2. So by some gymnastics, I can make sure that by the marked Lyapunov spectrum, actually by knowing the Lyapunov exponents of these orbits Hn, which converge to 1, 2 in this sense, they are homoclinic to 1, 2, I can actually obtain some information about the jet of the billiard map, because I know all the Lyapunov exponents of all periodic orbits which are nearby. So I get not really the jet of the linear map, I get the Birkhoff normal form of the billiard map. And by the Birkhoff normal form, if I have the Z2 times Z2 symmetry by an argument of Colin de Vernier, I can actually recover the curvature, the jet of the curvature. This is Colin de Vernier plus Z2 cross Z2. I can come back to the jet of rho at 1, 2. But by analyticity, this is sufficient to get the geometry of these two pair of symmetric scatterers. As a byproduct, You can actually recover much more. You can recover the geometry of this one, but somewhat this is a detail which comes out in a proof. But that's the idea of what we do. Again, it's very much similar to what Zeldich does with a completely different ingredient, but we fish out dynamical quantities and obtain the Birkhoff normal form and recover the jet of the curvature. That's pretty much what I wanted to say.